Hello everyone, my name is Haroldo Lima Jr. and today I'm going to talk about black holes as laboratories for testing nonlinear electrodynamics. This presentation is part of the program of the 9th Amazonian workshop on gravity and analog models that occurred in Belém, Pará, in Brazil. This presentation is based on this Physical Review D, published in 2023 by Marco Aurelio, in collaboration with me, Haroldo, Pedro Cunha, and Luis Crispino. The basic outline of this talk is summarized here in the screen. So I'm going to first introduce the difference between linear and nonlinear electrodynamics, and I'm going to discuss the necessity to introduce nonlinear corrections to Maxwell's equation. Then I'm going to discuss some effects of nonlinear electrodynamics in flat spacetime first. Then I'm going to generalize the results to curved spacetime, in particular to curved black holes spacetimes, and then we are going to use black holes as laboratories for testing. We're going to think as laboratories for testing nonlinear electrodynamics. And finally, I'm going to discuss the shadow and the gravitational lensing of such black holes which are sourced by nonlinear electrodynamics. Well, let's begin by discussing the Maxwell electrodynamics, which is also known as the linear electrodynamics. Well, the theory of electrodynamics, which unifies the electric, magnetic, and optical phenomena, is described by these four equations here, which are known as the Maxwell's equation. The first equation is the Gauss law for the electric field. The second equation is the Gauss law for the magnetic field, also known as the law for the absence of magnetic monopoles. This law here is the so-called Faraday induction law, which tells us how a varying magnetic field induces an electric field. This last equation here is the so-called Ampere's law, with the Maxwell's displacement current. So this set of four equations, they describe all the electromagnetic phenomena in a unified manner. It can be shown that these four equations here, they can be obtained using a classical field theory approach, well, by defining this Lagrangian density here, which is essentially this scalar f. This scalar f is the contraction of the Faraday tensor with itself being this second order tensor here, f mu nu. Well, let's check some scales that are in accordance with Maxwell's theory. For instance, here on Earth. So I'm going to show here some scales for the magnetic field in some situations. For instance, the Earth's surface magnetic field, which is around 3110 to the minus 6 Tesla. And then a typical fridge magnetic that we put on the door of the fridge has a magnetic field around 510 to the minus 3 Tesla. The strongest steady magnetic field on Earth is around 45 Tesla. And this value here, this steady magnetic field, was achieved by this steady high magnetic field facility that is a facility based in China and established the new record for this value here of the strongest magnetic field on Earth. So this is the scale that we are used to test Maxwell's theory here on Earth. Now, is it reasonable to assume that Maxwell's electrodynamics hold at any scale, meaning for even more strong magnetic fields? Well, we know that in the quantum scales, there are some evidence that new phenomena that are not predicted by Maxwell's electrodynamics, they arise. So in a very small scale, Maxwell's electrodynamics are modified. In particular, the theory to describe it is the quantum electrodynamics. Moreover, in astrophysical context, the electromagnetic fields, they are usually much stronger than the ones that I have shown in the previous slide. For instance, for these magnetars, the magnetic field are around 10 to the 10 Tesla, and just compare to the previous slide, so the strongest magnetic field is around 45, and these here, they can achieve 10 to the 10. So the scales are very different. And there exists the hypothesis that at very strong magnetic fields, the Maxwell's equation, they acquire some corrections due to these new scales here that are known as nonlinear electrodynamics, also known as NEDs. So nonlinear electrodynamics, they are corrections to Maxwell's equation that arises as a possible description of nature of electromagnetic field when the scales are around these ones here. Well, the first nonlinear electrodynamic model was proposed by Born and Neufeld, and that's why it's known as the Born-Neufeld model. It was proposed in 1934, and the motivation for this model is given here in this picture of the original paper. So Born and Neufeld, they say that the failure in the present theory, in this case, the theory of Maxwell's electrodynamics, may be expressed by the statement that it violates the principle of finiteness, which postulates that a satisfactory theory should avoid letting physical quantities to become infinity. So what is one example of quantities that become infinity in Maxwell's electrodynamics? Well, here's one example. We know that the electric field associated to a point charge is proportional to 1 over r squared. We can compute, for instance, the energy density associated to this electric field, which is essentially the volume integral of the square of the electric field. And when we compute this integral over the whole spacetime, this goes to infinity. So this essentially says that the self-energy of a point charge is infinity in Maxwell's electrodynamics. And then, motivated by this, Born and Neufeld introduced this Lagrangian 1.2 in order to avoid such quantities to become infinity. Another model that was proposed in 1935 is the so-called Euler-Heisenberg model. Well, their motivation to propose such modification of Maxwell's theory is traduced here in the following way. So, according to Dirac's theory of the positron, an electromagnetic field tends to create pairs of particles, which leads to a change of Maxwell's equation in the vacuum. These changes are calculated in the special case that no real electrons or positrons are present, and the field varies little over a Compton wavelength. The resulting effective Lagrangian of the field reads this equation here. So here we have the usual Maxwell's Lagrangian, the linear electrodynamics, and here we have nonlinear corrections to Maxwell's theory. So the motivation for this is the weak field limit of Dirac's theory. Well, it happens that we can consider in general a nonlinear electrodynamics by assuming that the Lagrangian density is a generic function of the function f, of the scalar f. And it's reasonable to assume that in the weak field limit, in the weak electromagnetic field limit, the Maxwell's electrodynamics is recovered, meaning that this function here, as f approaches 0, this is just approaches f. In this way, we have a generic nonlinear electrodynamics. And what kind of effects the introduction of nonlinear corrections to Maxwell's equation gives, for instance, to the propagation of light? It's well known that these nonlinear corrections, they affect the propagation of electromagnetic waves, as I discussed in this slide here. So the field equation for a generic nonlinear electrodynamics given by this L of F is given by these two equations here. And it can be shown that if we consider electromagnetic waves in the equinal limit, meaning the limit where the wavelength of this electromagnetic wave is very small in comparison to the scales of the problem that we are analyzing. And in this limit, it can be shown that the waves, they do not propagate in the background geometry, in this case, in the flat background geometry, the Minkowski spacetime, but they propagate along this effective geometry here. So this effective geometry depends on the properties of the electrodynamics, of the nonlinear electrodynamics, such as the first derivative of the Lagrangian with respect to the field F, and also the second derivative. Just as a curiosity, this effective geometry here is akin to the effective geometry in nonlinear optics. But what happens when we consider curved spacetime instead of in the place of a flat spacetime? Well, we can compute, for instance, charged black hole solutions which are sourced by nonlinear electrodynamics. So they are minimally coupled to general relativity. The Lagrangian is given by this term here, so it's the rich scalar minus the Lagrangian for the nonlinear electrodynamics, and we can show that the propagation of light rays around black holes sourced by nonlinear electrodynamics also follows an effective geometry. So light rays, they do not follow, for instance, no geodesics, they do not follow the geodesics of the background geometry, G mu u, but they follow the geodesics of this effective geometry here. And again, these light rays, they are going to follow these different geodesics, and this can change, this can modify the shadow and the gravitational lensing of such black holes sourced by nonlinear electrodynamics. So we can use black holes as laboratories for testing nonlinear electrodynamics, for instance, by observing their shadows. Well, in order to analyze this effect, we could not do things in general for a generic L of F. Instead, we have chosen a particular model, a particular black hole model, which is the so-called Diminikova black hole model. So this black hole model is given by this expression here, where this M of R is this function here, which depends on the Q parameter, which is essentially the electric charge of the black hole. So we are dealing with electric charged black holes in nonlinear electrodynamics. This function M also depends on this parameter alpha, which is a parameter that appears in the Lagrangian of this black hole, and also depends on the radial coordinate. This radial coordinate here is akin to the Schwarzschild spherical coordinate system. The event horizons are located in these points here, where 2m is equals to r, and we denote it as r plus. Well, now we can analyze, we can study the propagation of light rays around this Diminikova black hole solution. We adopt here the Hamiltonian approach by defining this Hamiltonian here, which is related to the effective metric, not to the background metric. And due to the existence of two conserved quantities, which are the energy and angular momentum of the electromagnetic wave, we can describe the motion of light rays in this geometry by this radial equation here. So it's essentially reduced to the problem of a central force, where these two functions f of p and h of p, they are related to the background model. And this U of R is the effective potential for the motion of new geodesics in the effective geometry. Here in this figure, I represent the function U of R, the effective potential for light rays trajectories, as a function of the radial coordinate for different values of the charge. The values of the charge, they go to 0.2. Well, they can also be 0, but the maximum value is q equals to 1. So this small q here is the normalized charge, which is essentially the charge of the black hole divided by the extremal value. And we notice here that this effective potential, one key feature is that it admits always a maximum point here, which is related to unstable circular orbits for light rays, which are also dubbed as light rings. So these light rings, they are related to the edge of the shadow of these black holes, these Diminikova model black holes, in the following way. If we shoot light rays in a distant way here from the center of the black hole, these light rays, they are going to be bent and they are going to be scattered to infinity. If we decrease the distance between the scattering center, in this case the black hole, and in the direction that we shoot the light rays, we are going to approach this red curve here, which is the unstable circular photon orbit. So meaning that any perturbation here, the photon tend to either escape to infinity or to fall into the black hole. If we decrease even more the distance between the black hole, the scattering center, and the initial direction of the light ray, the light rays, they are going to be absorbed by the event horizon. So this region here, which is delimited by this red curve, constitutes the edge of the shadow of the black hole, the shadow region of the black hole. And that is exactly what we show here. So we show the shadow edge of the Diminikova black hole for different values of this normalized charge. For q equals to 0, we recover the Schwarzschild result, the standard Schwarzschild uncharged black hole geometry. And as we increase the value of the charge q, this radius of the shadow edge decreases. So as we increase this charge, the shadow associated to this Diminikova black hole decreases. We have also performed backward retracing simulations using the effective geometry. So we generated these simulations here, beginning with the Schwarzschild case, where we notice here this dark region at the center, which is the Schwarzschild black hole shadow. And as we increase the value of the normalized charge, we notice that the shadow region decreases. And also the gravitational lensing also changes. But, well, what is the result when the effective geometry is not considered? For instance, we compute the new geodesics of the background spacetime and not the effective geometry. In a certain sense, we do not consider the nonlinearities of the electromagnetic field. Well, we show here in this figure the comparison between the size of the shadow computed using the effective geometry and the background geometry in this red curve here. We notice that this ratio between the shadow radius computed using the effective geometry and the shadow radius computed using the standard geometry or the background geometry is always greater than 1, meaning that the shadow edge computed using the effective geometry is greater than the shadow edge computed using the background geometry. We're going to explain this phenomena in a minute. Moreover, we also compared the shadow radius of the effective geometry and the shadow radius of the Horizon-Nordstrom solution, which is the black hole solution for a linear electrodynamics, meaning that the Maxwell's equation, the Maxwell's theory, coupled to the general relativity. So we have this behavior here. But now, what explains the fact that this ratio here is always greater than 1? Well, in the paper that I have mentioned in the beginning of the presentation, we have shown that the motion described by this effective geometry, so this kind of effective geometry that we introduced to describe the propagation of light rays in a nonlinear electrodynamics, is completely equivalent to the motion in the background geometry, but in the presence of a force term, which I shown here. So the physical interpretation for this result here is that the nonlinearities of the electromagnetic field introduces some self-interactions as the photon, as the light rays propagates, and these self-interactions, they manifest as this force term here. So this is the effective result. And we have done some simulations using this equation here that we have obtained. And we show this result here where we shoot a light ray and a massless particle which do not feel this force term in a similar initial condition, so in the same position and in the same direction. And we notice here that the light ray, which feels this force term, is absorbed by the black hole, while the massless particle, which do not feel this force term, is scattered. So we also have plotted this force term here, and we have shown that it is always negative, meaning that the light rays, the trajectories of photons, they feel this additional attractive force, and then they fall into the event horizon in comparison to massless particle which do not fall. And here we have essentially a similar result, but now with the maximum value of the normalized charge. So that's what explains the fact that the shadow is always larger when we compute using the back effective geometry due to this force term here. So the additional attractive force. Well, now going to the final remarks of this presentation, we have studied nonlinear effects of electrodynamics that arises in several contexts, such as quantum electrodynamics, nonlinear optics, and in other situations. So this is the hypothesis in strong enough magnetic fields, electromagnetic fields. Maxwell's equations, they maybe acquire some corrections. And we also have discussed that in the presence of a nonlinear electrodynamics, the electromagnetic waves, they propagate according to this effective geometry. And we have shown that this interpretation of the effective geometry is equivalent to the existence of a force term, which arises due to the self-interactions of the theory due to the nonlinearities. And we have studied how this propagation of electromagnetic fields ruled by this effective geometry, or this force term, modifies the shadow and the gravitational lensing of black holes. And in particular, we have studied the results for the shadow and the gravitational lensing of a nonlinear electrodynamics of a nonlinear black hole sourced by nonlinear electrodynamics, which is the Diminikova model. Well, I thank you for your attention, and I also pointed out that our results, or the results of this paper, are available free in this archive here that I show in the screen. I also acknowledge to the sponsoring agencies which are shown here in this slide. Thank you very much.